So compressor turbine matching is another important parameter in the aircraft engine because turbine produce enough power to drive compressor. So the compressor is driven by turbine while operating with safe temperature and flow limits. So the main importance of compressor turbine matching is to ensure power balance, to prevent shaft overspeed or underspeed, and to maintain engine efficiency, and finally to avoid mechanical failure of the system. So on compressor turbine matching, the law of conservation of energy is applied in order to a compressor that is driven by turbine on the same shaft. So the same shaft is used to drive the compressor. So this figure actually illustrates the schematic drawing of compressor turbine rotating assembly. As we see, once the turbine is rotated, and then it is connected with shaft, so that the shaft helps to rotate the compressor back to the cold section. And the RPM of this shaft is determined by omega, which is 2 pi n. And this TS diagram indicates the pressure and temperature condition at each section, section 2, 3, 4, 5. Okay, so as we know, section 2 is cold section. So as it enter into and pressure also there, it is the ambient condition. So once it enter, the temperature increase as well, the pressure increase, again so on. So this diagram indicates that. And from the power balance or the energy balance equation we have, QC is equal to M naught dot times HT3 minus HT2, which is also equal to NM times QT. Okay, Q is actually power here. Again, efficiency NM is there, which is equal to M naught plus MF, that is the fuel oxidizer mixing condition at the force point, that is burner exit area, and which is times HT4 minus HT3. So just simply dividing the above equation by the air mass flow rate and the total enthalpy at the engine phase, what we get is tau C minus 1 times the engine efficiency neta M times 1 plus F, the fuel to oxidizer ratio, the whole times CPT over CPC times T4 over T2, the whole times 1 minus zeta of turbine. So we are relating the zeta of compressor with zeta of turbine. Actually, that is the compressor O D ratio to the compressor D ratio, they call it. Anyways, it is not as such critical for us. Let's proceed for the next. So in our matching condition, the command shaft between the compressor and the turbine has the same angular speed. So the shaft is common so that their angular speed is the same. So the angular speed NC2, which is equals to the N divided by theta 2, radical of theta, temperature ratio at 2. That is for the compressor, which is the same, so that N divided by radical theta 4. NC4 is equals to N divided by radical theta 4. So NC2 and NC4 are the same. So what? We can relate it. N divided by radical theta 2 equal to N divided by radical theta 4. So we can get the relation between NC2 is equal to NC4 times radical of temperature T4 over temperature T2. This is the relation between the compressor and turbine matching condition. The work is proportional to the square of shaft speed. Work W of the compressor is proportional to shaft speed. Okay, from that, what you can get is the corrected shaft speed is obtained by NC2 is related with proportional to zeta C minus 1 proportional to NC2 square. So finally, we can relate them as NC2OD over NC2D, which is equal to radical of TT4 or TT2 over T. So that are the temperature. They are dependent on temperature only, actually. And the mass flow rate at the compressor and the mass flow rate at 4, which are also related with these corrected factors. So all the corrected factors will come into picture here. Okay, so this is just the relation between. Here, what we observe is the compressor and turbine performance mapping using the component matching condition. So this indicates the compressor pressure ratio in the vertical axis and the compressor mass flow rate. Okay, in the compressor, pi C indicates compressor pressure ratio. MC2 dot indicates the mass flow rate at the compressor. Actually, it is the air flow rate there. In the compressor, we have air only. So, which is given here. And you have operating line. The bold line indicates operating line. And every contour here are indicating the surge or stall contours. And NC, the zeta C is the efficiency, which is constant contour. The efficiency at constant contour is given. The second B indicates turbine performance map. So the difference between turbine and compressor is compressor is operating with cold gas only. Turbine is with the hot gas now. So what happened? Here it is reciprocal, 1 over pi T. That means pressure ratio of the turbine. And the horizontal axis here represents not only the mass flow rate, but it is mass flow rate times the RPM, the revolution per minute of the shaft. So MC4 dot times NC4, which is the unit itself is kilogram per second times RPM, revolution per minute. Okay, and we can see the counter of efficiency counter. Constant counter of efficiency is observed here. All of the contours are in the horizontal axis because our operating line is horizontal. Okay, but the operating line in the case of compressor performance map is in inclined plane. Not inclined, but it is kind of exponential. Okay, so we can observe for choking condition, M4 is equal to 1 is choking condition as a turbine. Okay, so that is given here. And now, based on what we have discussed, let's discuss some examples. Let me take one example. So it says a compressor performance map is shown in figure below. And the nominal operating line, which is a straight line, corresponds to TT4 to TT2, which is equal to 6. And the turbine performance map is also shown, and calculate and graph the gas generator pumping characteristics as a function of NC2 over NC2D for NC2D, which is 14,000 RPM. So these are the both equations, both graphs, as we have discussed here. They are given. So how we can perform it? In order to solve this, we can read the compressor pressure ratio, corrected mass flow rate, and the adiabatic efficiency as a function of corrected shaft speed for the compressor performance map. So the performance map is given here. NC2 is given 14,000, 13,500, 13,000, 12,500, 12,000, 11,500. It is, we multiply it by 1,000 here. Again, pressure ratio as a PICE is the compressor pressure ratio. Compressor pressure ratio is given. It is unitless quantity here. The MC2, that is the compressor mass flow rate in kilogram per second is given, 20, 18.1, and the compressor efficiency is given, okay? 82%, 84, 83, 83, 84% are given. So this is the table. Therefore, to calculate, we can calculate TT3 to TT2 or tau C. That is the temperature ratio at the compressor at each corrected shaft speed. For that, we have this relation. Tau C is equal to 1 plus 1 over zeta C, the whole times the pressure ratio, the power of gamma of the compressor minus 1, the whole over gamma of the compressor minus the whole 1. So this is the equation. Again, from the energy balance equation, we have the fuel flow parameter, just considering the energetic characteristic of the fuel, okay, and the efficiency and the CP values. Finally, we can get this kind of relation. Okay, TT3 over TT2, which is zeta C, as we know. This zeta C is the compressor temperature ratio. So we can correlate them and substitute values from the previous picture or the previous table. So that zeta T is equal to 1 minus CPC over CPT, okay? The whole times zeta C minus 1 over neta M1 plus. So actually, these are kind of intricate kind of formulas that may confuse you. So I will give you some important formulas during the exam moment. The only thing which I expect from you is to apply numbers. Actually, data and formulas should be given to you. Based on that, you will calculate actually. Simply looking this one, it is very difficult for you. So after certain rearrangement, actually gamma of turbine given 1.33 because that is hot section. Gamma of compressor is 1.4, that is different. So we can find some result. Temperature T4 to temperature T2 is equal to 6 is the result. So I don't know. It is not as such easy at far distance to explain these points. Anyways, this is a kind of example for this kind of problem. So what is the next? It is just okay. Yeah, I'm just facing some kind of. So it is just turbine afterburner variable geometry nozzle matching. This is when we are having an aircraft with afterburner. So that an aircraft with afterburner is military aircrafts like which needs additional power in order to operate with critical condition. so that such kind of aircrafts are only there in military. So it is critical stage in high performance engines like turbojets, low bypass turbofans with afterburners. And it ensures that the hot gas leaving the turbine can pass safely through the afterburner and nozzle while producing desired thrust. So once the hot gas come from the combustion chamber past the the turbine, then further combustion take place on the afterburner. So that is additional duty. So why it is important? It ensures afterburner ignition and stable operation to maintain turbine outlet condition with desired limit, and to allow maximum thrust modulation using variable nozzle geometry, and prevent turbine overheating or flow choking, and maintain engine performance. So that is the need. ሜቢ እዚህ ጋር ከዛ በላይ ብዙ መሄድ ብዙም የሚጠቅመን ሆኖ አልተገኘም። ለጊዜው ይሄ ይበቃናል። So these are actually the discussions related with afterburner. Okay, so afterburner የምናይ ከሆነ M4 we have M4 conditions and we have M8 conditions. So M4 is equal to M8 means what? M8 is equals to M4. ስለዚህ ያን እንትን የምንልበት ነው። M8 ማለት አፍተር ባርነር እዚህ ጋር ስላለ ነው። this is after burner. Okay, after turbine you have after burner and then exit. So this is kind of relations. Another important here is area ratio. So area of the turbine inlet, no, compressor inlet, and the area of the afterburner. So we use continuity equation on that. Maybe area relation is obtained from this formula. Okay, so engine of design analysis is our next topic. Okay, engine of design analysis, our next topic. So of design analysis states the performance of engine at operating conditions other than the design point. So every engine is designed for some performance parameter, but if it is designed, if the engine is work other than the design point, then it is of design analysis. Okay. For example, the of design parameters like altitude, speed variation, altitude variation, the throttle settings, which are called of design parameters. So aircraft engines operate at their exact design point, except in ideal conditions, which is of design analysis is essential for such realistic performance prediction. So engine operates at takeoff, at climb, at cruise, and at descent, not just design conditions. There, the climb condition needs excess power. The descent condition needs less thrust. It needs less thrust. Okay. The takeoff condition needs a critical takeoff speed of the aircraft that are performance parameters. Therefore, these are off design points. Okay, so predicting the thrust, the fuel consumption, the efficiency, and the temperature limit of all design points are very important. So in order to ensure a stable operation without compressor surge, without turbine overload, without flame out or flame fluctuation of the fuel burning rate, that is our off design condition. So the known set of design parameters for a turbojet engine in the off design analysis are design flight condition, design compressor pressure ratio, PIC, Ideal heating value of fuel. QR is the energetic property, which is the heating value of the fuel, a specific fuel. Again, design turbine inlet temperature, T4, TT4, or we express it in terms of theta of lambda, no, the zeta of lambda. Again, design component efficiencies like pi d, EC, pi b, neta b, ET. So these are this efficiency related parameters. Design nozzle exit pressure or area ratio, pressure ratio or area ratio. Gas properties, gamma, CP, gamma at the compressor, gamma at the turbine, they are different, that's why. CP at the turbine, CP at the compressor, they are different because one is hot section, another is cold section. So for the cold section, we can take a standard atmospheric gamma value, that 1.4. Again, design corrected mass flow rate, MC2. Design corrected shaft speed, NC2. Design axial Mach number at 2, which is MZ2. So these are the of design parameters. Okay. Look, this is the schematic diagram of turbojet engine, which indicates the station numbers and design parameters. Okay. The ambient condition, the inlet condition, okay, the compressor condition. Here we can see compressor here. So different conditions in the compressor we can observe. At the inlet we have axial Mach number MZ2, pi d or zeta d in the inlet. As a compressor pi c, we have zeta c or efficiency EC. Okay. As the burner, fuel flow into the burner is there. Temperature 4, QR, that is the fuel property. Neta B, pi B, these are the parameters inside combustion. Then after, within the turbine, what we can see, zeta T, ET, NM, zeta M actually, CPT, gamma T, that are different. Then after you can see on the afterburner, convergent, divergent nozzle condition also there, afterburner also there. So these are all the parameters. Okay, so we have also example that are related with of design parameter. So actually just go through this example by yourself. It is there on the book itself. Okay, so yeah, these are the solutions for that question. And I think it is better to finish our discussion here. Okay. So what are the steps in of design analysis? One is select flight condition. That is select altitude, Mach number, ambient temperature. The second step is estimate corrected inlet conditions. For each section, corrected inlet condition. Third is determine of design mass flow and shaft speed using component maps. And the fourth is adjust fuel flow and nozzle area to meet the required thrust. The fifth one is check the limit, the surge margin, the turbine stress condition, and the final is iterate your result until all components are matched to each other. All the pressure conditions is matched, all the temperature, all the parameters are matched to each other. So this is just of design analysis space. Maybe there are some worksheet questions from your textbook. So some of the questions I tried to put. So just go through these questions. Maybe they are important for us. Okay. And we have some short answer questions. just explain why component matching is essential in aircraft engine. List the three main types of component matching in gas turbine engine. What physical law govern engine component interaction? Just give at least 3 examples. These are just short answer questions. Again, so yeah, different short answer questions are there. Numerical questions also. An engine produce 200 Newton of thrust at an ambient pressure of this. Calculate the corrected thrust at standard sea level pressure. The second was the actual fuel flow of jet engine is given 0.5 kilogram per second at 250 Kelvin. Calculate the corrected fuel flow for reference. ስለዚህ ሌሎቹንም እንደዚሁ ጥያቄዎች አሉ እዚህ ጋር በተለይ ይሄ ወደ መጨረሻ ያሉትን ጥያቄዎች starting all the questions በቃ ይሄን ወርክሾት ጥያቄዎች በዚህ ቶፒክ ላይ መስራት ከቻላችሁ የሚፈልገውን መስራት ትችላላችሁ ማለት ነው so I think this is sufficient for us I don't know የተለየ ጥያቄ ከሌላችሁ በዚሁ እንጨርሳለን ይሄን ቻፕተር not only this chapter but will summarize our course so do you have any question because any question ለማለትም እንትኑ በጣም ሰፊ ከመሆኑም የተነሳ ሊያደነጋግራችሁ ይችላል ግን በተቻለ መጠን ይሄ መጨረሻ ላይ ያስቀመጥኳቸው ኤክስፕሌን አርግ numerical problem or something እነዛን clearly ተረድታችሁ ለመስራት ሞክሩ በእኔ በኩል so I can entertain some questions if you have hello
አቤት ዶክተር ይሰማ
ስለዚህ ጥያቄ ካላችሁ
ጥያቄ ዶክ ቴንክ ዩ እናመሰግናለንና ኮንቴንቱ ትንሽ ቫስት ነው እና ከቻፕተር 1 እስከ 6 ነው የምንፈተነው ይሰማል ዶክ
ይሰማኛል
እንዴት ነው የምናደርገው ከቻፕተር 1 ጀምረን እስከ ዛሬ ነው ወይስ እንዴት አድርገን ነው የምንፈተነው ለማንበብ
ባለፈው ቻፕተር 1 and 2 ሚድ ላይ መጥቷል አይደለ
አዎ እሱ መጥቷል
ስለዚህ ከዛ አካባቢ ሜቢ ሲምፕል ኮንሰፕቹዋል ጥያቄ ይኖርና ኦኬ ስለዚህ ሚቲንጉን እንትን ላርገውና ዲስከስ ብናደርግ ይሻላል ሪከርዲንጉን ላቁም